Well, good evening and welcome to Kopernik Observatory. My name is Drew Desker. I'm the director here at Kopernik. It's great to have a nice crowd even on a rainy night. So clearly it has a lot to do with I think the topic we're going to be entertained with this evening. Let's see here. I always like to start out with who's here for the first time or hasn't been here since your fourth grade field trip? Okay, a few people. All right, who here are members? Pretty much everybody else, that's great. So the people who just put their hands up first, I want to just mention that Kopernik, we're a nonprofit organization, but we have a membership, and we belong to what's called the ASTC, Association of Science and Technology Centers. It's a consortium of over 350 other science centers that honor each other's memberships. So with a Kopernik membership, you could go to Robertson, you could go to the Science Center in Ithaca, the Museum of Science and Technology up in Syracuse, you could go to Franklin Institute down in Philly, or the Intrepid down in New York City. And you get to walk in for free. Actually, a few years ago, I brought my daughter down to the Franklin Institute. And had we just paid for myself and my daughter, we would have paid more than a full year's membership up here. So it's certainly worth considering. If you like this kind of place and want to support Kopernik, consider getting a membership. So on our website, we always keep you up to date with what's going on. So we always have so tonight's topic is going to be the robot seeing eye dog, the autonomous intelligent robotics. If you actually, let me grab my mouse here, and if I go to the right, there we go. What did I do? I just made that go away. All right, let's try that again. If you go over here to program and events, you can go down to public programs, and you can see the upcoming programs. So tonight's a robotic dog. Next week's going to be another robotics presentation, but this one is actually going to be a bunch of high school students. There's a Southern Tier robotics group that meets and every year puts together a robot. Let me see if I can jump in here a little bit. You can see it a little bit. Actually, that is about the biggest. I can see that particular image. But anyway, that robot, you can see the picture of the students. So it's a substantial sized robot, and every year the competition requirements are different, so they have to build a robot up from scratch, and so they'll bring that up here and they will talk about that. Any of the students here today? All right, maybe they're still working on the robot, and but anyway, if we go back to our homepage, we have a couple of other things coming up. We actually have a 5K race, so any of you runners or walkers. We even invite the walkers to come. It's a 5K race, but it's on the flat part up here. We don't make you go up that big hill. And it's a lot of fun, and we do it toward the evening so that hopefully if the skies are clear afterwards, you can look through our scopes. And also next week, next Saturday, we will actually be holding our what's called a Brain Day. This is graduate students and faculty from Binghamton University Psychology Department doing some hands-on activities for students that deal with the brain. And also we'll be announcing and opening up our registration for our summer camps. And we have a very extensive summer camp program for students literally that are currently in first grade, maybe going into second grade, all the way up through high school. One of the camps that I run is called Welcome Aboard the International Space Station. And it's for rising 5th and 6th grade students. And they'll learn about what kind of training astronauts go through, what kind of work they do on the ISS. I talk about radio communication and satellite orbits, and part of that week, we will actually have our students talk to an astronaut using the ham radio station we have here at Kopernik, talking directly to the ham radio station on the ISS as it's flying by. So our students have about 10 minutes to ask their question as the ISS flies by, and so that's one of the camps we'll be doing this summer. So we have a lot going on, but what I really like about, I mean, I like many things about Kopernik, but I really love these programs on Friday night because it's really an opportunity for us to sort of continue our education. I mean, it's, and I'll tell you, all you people that are currently in school, learning doesn't stop in 12th grade or when you finish your graduate work. It really should be a lifelong effort that you should be wanting to know what, how do things work, and that's really what Kopernik's all about. One other program I like always to talk about is our Girl Power program. So twice a year we run a program for girls between 3rd and 8th grade, and we'll be talking about a particular topic of either in science or engineering, and we always have a female subject matter expert talk about the work that she does, in that field. And as part of that, talk, our girls get to talk and get to ask questions of that person. So a few years ago, we actually had a NASA astrophysicist talk about the work that she does at NASA, using satellites to collect data about carbon dioxide levels and how that affects global warming. And then one of our girls asked during the Q&A section, how did you get interested in astrophysics? Now again, these are 3rd to 8th grade students. And I loved her the scientist's answer. She said, well, when I was in college, I was an English major, but my boyfriend was a physics major. And we'd go from observatory to observatory. I eventually dumped the boyfriend, but I kept the astronomy. Now she has her Ph.D. in astrophysics and works at NASA. So you never know where a seed's going to get planted. But again, these Friday night programs are really an opportunity for us to continue to plant some seeds. And who knows if it either turns into a career or just makes us a more informed person. So we're very fortunate that we've got a fantastic educational facility here in the southern tier of Binghamton University. And we've had a number of faculty and students come up to do presentations on the work that they do, and tonight is one of those nights. So Professor Shiqi Zhang and his graduate student Dave Defazio is going to talk about their project that they've been working on for some time, and I'm not going to step over that. So let me just get the computer moved over to his computer, and we'll take it from there.
Sure.
All right. And give us a second, and there we go. All right. Thank you.
All right. Yeah, a lot of things happening here. It sounds really exciting. It's my first time being here, so it's really a new experience, and it's super happy to see all of you here. And thanks, Drew, for the introduction, and thanks, Cash, for connecting me to the Kopernik to meet you guys here. And hope you enjoy the next hour on AI and robotics. Okay, so overall, the plan is that I'll talk about some general AI and robotics research for maybe half an hour. And then my PhD student, Dave Defazio, will talk about his work on robotic guide dogs. And he will demonstrate the robots. I know you can't wait to see how the robot works, so I'll be quick. Okay, so I'll start with some general artificial intelligence and robotics ideas, and then talk a little bit about our recent research. So you must have seen like AI everywhere, right? Movies, TV, newspaper, website, everywhere. So some of them are very negative, and some of them are super smart and sensitive, and some of them are doing things really good. But the general misunderstanding is that AI is usually going to one extreme or the other. So what I'm trying to do in the next half an hour is that maybe give you a more objective idea, like what AI is about. When AI researchers talk about AI, what it's technically about. So those are just some movies, Terminator, artificial intelligence, and some of some movies. Okay, so I won't be too technical, but this slide will be a little bit technical. So some hypotheses about what artificial intelligence is about. One hypothesis is that AI is about developing agents that think like like people. This is one hypothesis. And another hypothesis is that AI is about developing agents that act like people. Do you think those are good hypotheses? Yes? Okay, let's continue. So another hypothesis is that AI is about developing agents that thinks rationally. Okay, there's a concept, rationality, but AI is about, so those are just a few hypotheses. Later I'll tell you which one is. So the last one is AI is about acting rationally. You can see that there is a happy agent here. So actually this is what we mean by AI when we talk about the technical details. So I'll give you some reasons why the first three are not the case, okay? So AI is not about mimicking human thinking. One of the reasons is that we don't really know how humans think, okay? There's a neuroscience and psychology, a lot of theories, but we really don't have a very good idea about how human thinks. And AI is not about how to act like people. Especially for recent years, AI are doing better than people in many ways, like image recognition, natural language. There are benchmarks like where AI are doing even better than people. So it's not about how to act like people. AI is not about thinking rationally, because in many cases, AI does not think about in the very rational way, but it can do good things. So we still think this is a good agent, okay? So technically, AI is about acting rationally. So that's how AI researchers think about artificial intelligence. I guess this is probably too technical. We'll soon get into some fun videos. All right, so acting rationally, that's a point of artificial intelligence. And next, I'll quickly go through some tasks. And let's do a quick quiz and see if AI can do that, okay? So the first one is, can AI play a decent game of table tennis? Yes, right, AI can do that. Can AI do a decent game of Jeopardy? Yes, this is from IBM. Actually, IBM started from this area. And AI can do a decent game of Jeopardy. Can AI drive safely along a curving mountain road? I see yes or no, yes or no. So the state-of-the-art AI can do that. So some people say it's even better than professional drivers, but it can do that. Next one, drive safely on campus. So this is a tricky part. A common misunderstanding is that driving on curving mountain road is more difficult, but actually driving in human environments is more difficult. So on campus there can be anything, right? There can be obstacles, there are people running. If it's an elementary school, there can be even more situations. So this is actually more difficult, and AI are not doing very well here. Then buy a week of grocery on the web, it's trivial, right? Can do that. Buy a week of grocery at Walmart. So that point back to the challenge here, because there are kids running around and there are objects on the floor and there are slippery milk spills and there are different things, so it's actually quite difficult. So not there yet. You see some cleaning robots in Walmart, but they are following the fixed path. So there are quite some constraints. But overall, AI robotics are not doing so well in those crowded environments. Then human champion in the Go game. So that happens a few years ago. Really a big milestone for AI community. And this is from Google, they have multi-agent collaborating with each other. It's just some visualizations about the state of art of AI technologies. So next, I will be a little bit more about AI history. Okay, so probably you can say 1990s is a time where before that, the whole AI field was largely driven by rules. So you say, if A is true, B is true, then C is true, something like that. That's before 1990s. And then from there are machine learning and data coming in, more and more data-driven AI. So it's about artificial intelligence, but under the hood, it's really changing a lot. So when we talk about classical AI, it's more representation. I have some knowledge. How do I give the AI my knowledge? So there's a representation and reasoning. So there's a so-called expert system. I don't dive into the details, but that's before, you can say, 1990s. And then more recently, the whole AI landscape has changed a lot. So it's more and more data-driven, a lot of images, a lot of text, a lot of videos. And so the goal is to enable intelligence without being explicitly programmed. So we don't tell agents, this is true, that is false. So it's more like large data sets. And machine learning and deep learning started playing a role. So it's more like a AI history, what I'm talking about right now. And there was the ImageNet, which is including millions of images. And before that, all the data sets was thousands of images, but ImageNet was more than 10 years ago. So there were millions of images. And then AI can do object recognition, say, is there a cat in this image? Right now, it's for this kind of task, AI can do better than people. Okay, surprisingly, AI can do better than people. So this is a current data-driven AI age. And if we talk about maybe the past couple years, so there's a so-called, people call it large language models, vision language models, or more professionally, you can call it foundation models. So then it's not just a large data set, it's huge, right? It's millions of parameters, and you can learn from the internet scale data set. So then AI can do even more. For instance, so right now when you train a large model, this model can support many downstream tasks. Right? When you train it, I don't even know how people are going to use it. There are many, many downstream tasks. If you talk about natural language, it can be, say, translation, summarization, dialogue. So one model supports many different tasks. So this is one cool feature of foundation models. And you probably have, there's a ChatGPT, there's Google Bard, now Gemini, and Llama. There's Llama 1, Llama 2, and right now people say Llama 3 is coming out. So this is the year of the so-called foundation models, large language models. That happened just very recently. I guess for the younger generation, different schools have different strategies. Like some schools say, no, you cannot use ChatGPT for your homework, but some schools are more flexible. So people are learning how do we get used to large language models, right? Even at Binghamton University, there are some discussions. Should we let students use that or not? AI is changing how people learn and how people communicate with each other. It's happening right now. So this is about 2023, 2024. All right, so this is very quick summary about the three phases of artificial intelligence. What about robotics, right? The title is Autonomous Intelligent Robotics. Now let's change the topic a little bit. So robotics is a highly interdisciplinary topic, right? So robotics is about mechanical, about learning, about vision, about many things. But generally, there are three tasks. Okay, so we have a robot here. You're going to see the running very soon. This robot pretty much do three things. One is to sense. All right, so it uses camera to see who is standing in front of me. It's using this big thing. So they will talk about it momentarily. So to see like if there's an obstacle, and it's using a microphone to hear what you say, and it's using different sensors to sense. And then after sensing, there's a reasoning. So, okay, I receive all of these. I see a person standing in front of me, or two persons like standing facing each other. But what does that mean? So that is a reasoning task, right? To understand the environment. If two people standing facing to each other, that means maybe they're talking to each other, right? They're enjoying a chat, right? If there's maybe a bag in the middle of the floor, the reasoning step will say, oh, something is wrong. Maybe somebody left it there. So in general, there's a sensing, reasoning, and then the robot will decide, I should do something. Right? So there's a acting. So based on how the robot perceives the environment and the reasoning the robot decide, maybe I want to pick up this backend and give it somewhere, or maybe I should say, excuse me to make my way to go through the corridor. So generally there are 3 steps, and those are all quite challenging. Okay, and this is a NASA robot astronaut, so from Houston, NASA. Okay, so next I'm going to give you some quick images about different kind of robots. Okay, so be prepared. I'll give you some quick quiz. Okay, so one is from Boston Dynamics. It's a humanoid. Right? If you search on Google, you can find like many fancy videos doing dancing, doing moving objects, and this is like a parkour robot. And this is a Amazon warehouse robot. So right now for the fulfillment center, you can easily see like 1,000 robots working together, moving the shelves from point to point. And there's marine robots that can swim like a fish, and you have flying robots. So, and quick question. So, if you talk about this robot bird, what do you think? Like for this robot is particularly challenging compared with other robots. I mean, of course it can fly, but other than that, anything you can think of? Sorry? The weight, right? Great, yeah. So this is not like a, yeah, I'm surprised. So yeah, thank you. So if it's a ground robot, if you don't need the robot, you just let it stand there, it doesn't consume any energy, right? But if it's a robot bird, actually the weight, the power, and everything is a huge challenge. So people spend a lot of effort. How do I reduce the weight, make it able to maybe fly for half an hour or even longer? So that's a huge challenge. So great. And maybe, what about this one? The robot fish. Imagine that you are developing this robot and waterproof. Yeah, good point. Any other challenges? Yeah.
Flotation.
Sorry? Flotation, right? Yeah, great. Anything else? So think about, you are developing a robot fish. Is there one thing that you are really worried about compared with the other robots? Yeah.
Navigating like the environment.
Navigating the environment, right? We're getting closer and closer. Okay. So I'm not a marine robot expert, but I talk to people working on these robots. I ask, what do you think is the main challenge? They tell me that, okay, the main challenge is that every time I put this robot into the water, I'm afraid that this is my last time seeing it, right? So because, I mean, if it's a ground robot, it won't escape, it won't disappear. But if it's a marine robot, localization, navigation, there's a current, there's a, sometimes the water is really muddy, and it's the communication and the localization is very challenging. So this is sort of a unique challenges. And there are all kinds of challenges. For this robot, balancing itself is very difficult. For Amazon robots, there are hundreds of them. How do they coordinate? They don't run into each other. They do the job they're supposed to do. So there are all kinds of challenges. I'm trying to convince you that it's a challenging field, and there are a lot to work on, and hope that when you go to college and you probably contribute to the field. So generally, it's a very difficult, and I need to speed up. So perception is difficult, actuation is difficult, and they make all kinds of mistakes, right? So I should do this, but hey, it's really difficult. So robotics is difficult. If you send a robot to the Mars, and then sending one message there will take up to 20 minutes for the robot to receive it. So autonomy is really, really important. Right? You don't want to ask the robot to ask you how to do something. The robot must be by itself. So it's difficult, long-term autonomy. And this is like Intel has hundreds of robots. They together form this Intel. So you can imagine a lot of coordination is needed, the communication, the real-time performance. This is quite difficult. By the way, this is not CG, this is real, okay? Yeah. So I'll skip this part. There are quite some active topics. I will maybe play a couple videos. And so generally, we are interested in robots that interact with people, serve you guys, and learn from this experience, because robots make all kinds of mistakes. And we're not alone. There's a community. So next, I'll just play a few videos that I think are sort of representative of our research, and then I'll hand it to Dave. So I'll start with this one. So this is like more than 10 years ago. When I was a PhD student, I worked on this small robot. It's called erratic. It was indeed quite erratic. And we were using computer vision to recognize objects, and it was using LiDAR to figure out where it is, okay, a fully autonomous robots. And what it was working on is to look for its friend, a humanoid robot. So then the robot used all the visual features. You can see this is the robot view, quite laggy, right? So right now robots can do much better. This feature-based method, quite laggy. And it go to the office. Oh, do I see my humanoid robot friend? It stop there and turn. Oh, it's not here. So then it decide to move on to the next place, and then finally I'll jump to, okay, it's entering my research lab, and there was a robot soccer field. You see that, oh, the humanoid robot is standing somewhere in the corner, I find you. So this is, from here you can see how robot sees the world, right? So it's laggy, it's using features, and this is what the robots feel. And this is how robot navigate. It was able to avoid obstacles, and it generate a path which is not very obvious, but there's a path the robot in mind. Okay, I want to go out of the room following this corridor. That's how what's happening under the hood. So this is one. I'll skip this one since we have this robot here live. I'll just leave it to Dave. This one. Okay, I'll talk about this one. All right, so this is a project we collaborate with a vehicle company, Ford, and we want this robot to deliver a cup of water. Okay, so then it was pretty recent, and we had the large language models, ChatGPT. So the robots think, okay, I can go there and find a cup and fill water and then serve it to somebody. But it turned out the robot go to the cup and find, oh, I'm in a situation I never anticipated. So what is the situation? There's something in the cup, right? There's something in the cup. So then robot doesn't know how to do it. So we develop a novel method to let this robot to ask GPT and say, hey, I'm in a situation where I never seen before. Can you maybe tell me what I can do? So there's a cup is occupied. And the robot asks GPT, how do I address this situation? And you will soon see that GPT gives the robot some alternatives. And GPT says, robot, tell me what other objects you have. And the robot say, I see a chair. Can I use a chair for drinking water? Ask GPT. GPT say, no, chair is not good for drinking water. Can I use a microwave? Can I use a bowl? Can I use a plate? And GPT is helpful and say, you can use a bowl for drinking water. So then robot has say, bingo, I found a new solution, right? So robot go to the bowl and grasp it. So using the arm, so this robot generate a trajectory for the whole arm, pick up this bowl and use it to serve water. So this is what we did last year. Walk to table, grasp bowl, walk to dining table, and put it down. Okay, I think I can probably stop here, but before that, we can have the transition. But when Dave is getting started, any questions or any comments? Yeah. Yeah.
What does GPT stand for? Yeah.
If I remember it right, it's pre-trained.
T is probably transformer. I don't know what the G is.
Transformer, but what is generative? Generative pre-trained. Yes, generative pre-trained transformer. Yeah, thanks.
Do I just put this in my pocket?
Any other?
In talking about the history, you said in 23, 24, things started to move so quickly. Why is that? I mean, all of a sudden, they were just flooded with it.
So again, the question is why all of a sudden it seems that the last year and this year that things have just skyrocketed forward in AI.
Right. So it's a really a multi-factor thing. We have more data, right? We have more powerful GPUs thanks to NVIDIA and AMD. We have like crowdsourcing platforms. We can easily get people together to generate new data sets. And we have, what is that? So computational power, we have data, we have all the training resources, and we have more advanced algorithms. So there are many AI researchers working hard to develop more efficient methods, and then we have like GPT. I want to say that the algorithm and the theory is not that new, but this is happening in recent years because of many other factors. Yeah. Thanks. Dave, go ahead.
All right, hi. So my name's Dave. I'm a student in Shiqi's robotics lab. And today I'll be discussing our work on like a robotic guide dog system. This is kind of a more fancy title. Oops. Oh, oops. All right, so the motivation of this work is to help visually impaired people navigate. There's a variety of different tools available for visually impaired people. A common one is to have like a guide dog, as you see in this image, where you have like a harness on the dog and you could hold on to it and the guide dog can navigate around and it could help people who have trouble seeing navigate. But there's a bunch of issues with that. For example, guide dogs are expensive. They take a while to train. There's a limited supply of them. Even they could be hard to take care of. You need to walk them every day. You need to feed them. Maybe I'm a visually impaired person, but I don't like dogs. So like there could be a need for different types of navigational aids. And in this work, we try to develop a robot guide dog system. So you could use a robot for this task instead. And ideally, the robot is cheaper and it's more accessible to a larger amount of people. And maybe it could even perform better in certain instances. So the typical guide dog setting involves a human holding a rigid harness connected to the dog. And when the dog moves, the human can immediately get feedback to understand where the dog is going. And it's the dog's job to navigate around obstacles in the immediate environment. So if there's like, you know, something blocking me right in front of me, the dog, it's up to the dog to go around that. But globally, it's up to the human to know where you are. So if I'm, you know, at some intersection, it's up to me to know if I want to turn left or right. And I need to communicate that to the dog. And that's typically done through short verbal commands. So I might say something to the dog like left, and the dog will know, okay, let's go left. And so for our robot system, we develop a tugging interface for human-robot communication. So the human can just tug the robot physically left or right, and then the dog would understand. So for example, you could tug it left, and then the dog should respond to that tug by moving left. So there's kind of a bunch of technical details as to how we made the system work. I'll just try to give a very broad summary. First, we need to figure out how do you get the dog to actually walk. And when you tug the dog, you want to make sure that it doesn't fall over. How could it be robust to different tugs? And we use a physics simulator. So imagine maybe like a video game, or you're on your computer and you have like some robot dog in the computer. And it doesn't know anything in the beginning, and it just takes some random action and it falls over immediately. Well, what we do is we leverage something called reinforcement learning, where slowly over time, you give it feedback. So okay, it falls over, and you tell it, that's not good. And over time, it learns to walk forward, and you give it external pushes in the simulator, and it could learn to be robust to those. And additionally, we train a force estimator. So just based on the sensors on the robot, it can estimate the direction of the external force being applied. And then we need to move from the simulator to the real world. And that's a common challenge in robotics. It's called the sim to real gap. There's a lot of research going on with that. And so you somehow have to take what you learned in the simulator and apply it to the actual robot on hardware. Maybe I'll skip some of the details of how we actually got it to work. But somehow we get it to work on the robot. And we have a force estimator. So you could just look at the signals at every time step. And if you see a peak in the signal, that means that there's a force that was applied. And based on that force, the navigation system knows, okay, now we should take a left because we estimated a left tug. And so I have a real-world demo video of our system. So the robot is walking, and it approaches an intersection. And we have a blindfolded human being guided now. So the human tugged it right, and the robot responded by making a right turn based on the tug. And okay, now we're at another intersection already. The human's going to tug it left. And it wasn't even that hard of a tug, but still it detected it and it responded. You could notice on the upper right-hand side, we have a map of the environment. This map was generated beforehand. We actually ran the robot through the entire floor of the engineering building. And the robot has a LiDAR sensor, so we could generate the map. If anybody doesn't know a LiDAR sensor, it shoots out lasers, and it tries to figure out what the surroundings look like. And then this LiDAR sensor is used to localize itself on the map as well. So that's how it understands where it is within the map. And so the robot is autonomously navigating this whole time, and it's just responding to the human tugging it. And the human can't see, the human is blindfolded, so just the robot is guiding them alone. Oops. And I'll maybe quickly go through this. We have some evaluation. Is the locomotion controller we learned, is the way it's walking, did we do that well? Or do existing approaches work better? So we check if we apply external forces, is our controller actually robust, or does some older approach fall over less? And it turns out, indeed, our controller doesn't fall over as much compared to existing works. And similarly, it drifts from the expected trajectory less than an existing approach. And we also evaluate the accuracy of our force estimator. So the robot has an accelerometer sensor. And some people might wonder, well, why bother go through all the effort of training a force estimator if you could just get those readings from the accelerometer? But the thing is, when the robot walks, it uses footsteps and the body vibrates, and the accelerometer readings are very noisy. And so if you look at this plot on the left, we could see the accelerometer signal, and the plot on the right, it's for the exact same trial. It's our force estimator signal. And we could see the signals more clear. It's more obvious on this graph where the forces are occurring. And so we find that our force estimator is actually useful when compared to just raw accelerometer readings. And so overall, our contributions is we developed a robotic guide dog system with a tugging interface for the human to communicate with the robot. And we trained a locomotion controller and a force estimator to do that. And we demonstrated this on hardware. We ended up getting some media coverage from a few of these media sources. And finally, we have some work in progress. So we're trying to build on this in a few different directions, and I'll just very briefly discuss one of them we're looking at now. It's to add a natural language interface. So if you have a real guide dog, you can't say anything more than very simple commands, like pre-trained. You can't just talk to a dog, right? So, but with a robot, you could add a microphone, you could add a speaker, and as Shiqi was mentioning, there's these large language models that exist that are really good at certain aspects of conversation. And so we try to leverage large language models where I could say something like, "I'm thirsty," and the robot will understand, okay, well, maybe you could go to a water fountain, or maybe you could go to a vending machine or something, and it'll also understand the surrounding environment and realize, okay, well, this environment has a water fountain, so maybe I'll recommend going to a water fountain. And you could have a conversation with the robot, and ideally you resolve your request, and then the robot will autonomously go to where you want to go. And so we just have a short video here demonstrating this.
Water fountain, or are you looking for a kitchenware? You might find beverages. To reach the water fountain, we need to open 2 doors. To reach the kitchen, we need to open 1 door. Navigating to the water fountain will take the shortest amount of time.
Take me to the water fountain.
Heading to the water fountain now.
So we just had a
Can you
conversation,
please open the door?
and now they decided to go to the water fountain to resolve the request.
We enter the room with many benches and tables.
And the robot talks to the human along the way to let the human know
Can you
what the
please
environment
open the
looks
door?
like.
We are in the main corridor. We have arrived.
Yeah, so that's our work, and that's everything I had to say about it. Thanks for listening. Yeah.
I'm curious why the interface is a tug when it would be the opposite, right? So if you're low vision, the actual
Hold on a second here. Let me just put you on the microphone. Who's asking the question? Sorry.
So I was wondering what the tug interface is. If you have low vision, isn't the guide dog tugging you in the right direction? So why do you have the tug of the dog?
Yeah. So yeah, it's a great question. The dog is tugging you in the right directions. At the same time, you'd like to communicate with the robot too. There's many different ways you could communicate with a robot. We felt like a simple tug left or right is one simple, reasonable way to do it. Also you could use language. Maybe there's some other ways to communicate with the robot as well. It's just one example of a simple interface. By no means is this like the best way or the only way.
So it's actually a collaboration system. So at a high level, the human is giving the commands to guide the robot. At the low level, the robot is guiding the human to avoid obstacles. So it's the bi-directional communication, both are important. Yeah.
Any other questions here? In the back here? Give me a second.
So I understand that guide dogs are, one of their most important tasks is intelligent disobedience. So in other terms, disobeying a command in order to make a safer, more correct decision. How capable is the robotic guide dog at performing such a task?
Yeah, that's an excellent question. We're actually looking into that right now. Currently, I would say not very capable. We're looking into using vision language models, so similar to ChatGPT, except also dealing with vision. So yeah, we hope in the future we could build on this, where the robot has a camera, and hopefully it could get like an actual understanding of the scene it's in. So if I tell it to do something, say I want to cross the street but a car's coming, then it could use vision and common sense reasoning to understand that we need to disobey the human. But yeah, as of right now, we do not have the capabilities. Yeah.
We'll probably get a better answer next year.
Yeah.
That's what we're working on now.
Okay, well, we'll invite you back next year to see how you've progressed here. You have a question?
How does the blind person know like when there's an intersection, or does like the robot tell you?
Yeah, that's a great question too. We kind of cheated. So in the real world, the blind person would typically already have a understanding of the environment. So they'll go through routes many times, and they'll just know where they are. For the purposes of this research, we actually had somebody else, some third person, say when to tug, just for like demonstration purposes of our system.
We have one question from the chat. It says, shouldn't the robot talk like Scooby-Doo? All right, well, I guess we're going to go to an actual real demonstration of the... Sony just changed to the camera here. And for those on the live stream, let me see if I can... There we go. I'm going to have to...
It's a bit short, so you can feel free to sit in the front if you want. Every time you start it, it must be in the start position, so it doesn't hurt yourself. This is the foot pose like it's resting, and I think it won't take long, right? Maybe
No, yeah,
few
like
seconds.
30 seconds or so, we'll get it up.
While we're waiting, I was wondering, it seems like the legs are very similar to that of a dog. Is there, was that purposeful, or was it, is there, you know, just because you're sort of replicating a dog, are you choosing to use that as the leg design, or is there, might there be another type of leg design that would serve the same purpose and maybe provide better navigation over?
So I think when they develop it, it's sort of a. I think when they design the robots, they considered like bio-inspired, but we are computer scientists, right? We're more like software and AI, so I can't really tell about the hardware part. Yeah. So, do you want to talk about it, or I do it?
Yeah, I don't know what to say.
Okay, yeah. So this is a robot. This is a LiDAR sensor. So it's very accurate. Project a number of beams and see how far it is away from the obstacle. And yeah, I'm not sure what that means.
He's waving hello.
Yeah, be nice.
Yeah.
So here you see the camera. We call it RGB-D camera. Do you know what D means here? RGB-D? Any other answers? It's depth. Yeah, I think someone mentioned depth, right? So it's depth. So when it's capturing an image, it's also knowing how far the pixel is away from it. Right? So it's used on different kind of robots. What is this? You just saw it. What is that? The speaker, right? So this is how the robot talk to people. And there's a battery here. There's you can lift it up here, and there are different kind of ports. That's a robot. So Dave has another line of research he didn't talk about, which is to use machine learning to learn different locomotion policies. So that's a pretty cool line of work, but it's more technical, and the robot can learn, I can, what is that, trotting,
Yep.
bounding, and diagonal, like pacing, different kind of gaits, and some are faster, some are more power efficient, and so we can do that. But right now, Dave is just demonstrating the default controller. So still it support, I think, what is that, higher walking, lower walking, and running, different kind of locomotion styles. Yeah. This is another one. A little bit noisy, right? Sorry about that. You think they can maybe try it?
Is it able to negotiate stairs?
Yeah, so the gate I just showed you, where it's lifting its feet up higher, it could do stairs up to 15 centimeters, so like pretty small stairs. But,
Well, yeah, stairs that you would normally find in a or not.
This robot with this setup, probably not a normal set
Okay.
of stairs. Other robots could do normal stairs. Right. This one can only do like shorter stairs.
Okay.
Yeah.
So this, yeah.
So for your accelerometer, talking about the stairs, if it goes up a ramp or something like that, does the robot then know to tilt itself forward to then adjust its gate to go forward?
Yeah. So that's what the controller under the hood is for. So it's balancing. Thanks. So maybe we can invite who wants to have a try of the controller? Just be very careful. The first, yeah. Could you maybe do some quick training like how it works?
Sure. Okay. This stick, you could go up, right, left, back. If you want to turn, do this, this. This is like the slow one. You could have it go faster, but maybe. I don't actually know. I'd imagine this top speed of any quadruped robot is like a little over 3 meters per second. This one could probably max out at like 2 point something.
So maybe you first and after you.
The battery life, if you're using the LiDAR
be the
sensor
next,
with
okay.
mapping and things, something like 30 to 40 minutes. Without that, like maybe like an hour or hour 20, something like that.
You can also try that one.
Yeah. So it's like right now it's teleoperated. Like in the video you saw, it was fully autonomous. Yeah, it depends what you want to do. Yeah.
I think one of you. Yeah. Do you want to try? I think one of you will send.
Yeah, go ahead.
You're the last, okay? Yeah. Anyone? Okay. Only these two, but
As far as the camera can see, or the LiDAR, it says the LiDAR sensor is 200 meters, but I don't think it would be very accurate that far. Yeah.
So people are using the robot for different applications, and we are more interested in everyday, like home environments. But people are using it for search and rescue, and the New York City policemen are using spot robots. So I don't know if you read the news, but actually, I think just a couple of weeks ago there was a first spot robot died for a human. So that was a different story. Yeah, sorry. This one is manufactured from China, so it's like an affordable version of the bigger ones, and we're using it for training. But so if you read the news, I think the Boston Dynamics spot robot is more popular because it's quite expensive. Yeah, we're trying to maybe get one in the future, but yeah, this is a. This one was actually a gift. So we just they think our seeing eye dog is good research, and I think it's a.
I think with this LiDAR sensor, probably like 15,000-ish.
Yeah.
The LiDAR sensor is
Something like
expensive.
that.
Otherwise, it would be like 10. Yeah.
Anyone else want to have a try? Yeah. Yes. You will be the last. Okay. Yeah. While they are trying, any other comments or questions?
So with the robot, let's say within a room like this, if you put it on autonomous using the LiDAR, would it be able to navigate the room? You told it to just circulate counterclockwise or something?
Yeah, so if we first run the robot around the room to build a map, then we have the map, and then it could autonomously navigate. Admittedly, with these chairs, it might be a little bit difficult, but yeah, it should be able to do that. You have a question?
I'm guessing that that one's the same on the video.
Oh yeah, this one is the same in the video. In the other video you saw, there was a black robot. Similar kind of thing, but yeah, a different robot.
Will we get to hear the voice?
Do we have the microphone with us?
No, yeah.
we didn't bring that. We have a headset thing that can talk to the robot. We didn't take it. We also didn't take the leash. We just,
You have a question? Oh, that's in our lab. We just brought the other one. Yeah, we have two of them.
okay.
All done?
Yeah. Any additional questions either here? We're done with the questions on the chat. If not, if something pops up, I'm sure they'll be happy to answer it for you after we're done. But especially for anyone who may be here for the first time, again, the rule here is you can't leave Kopernik until you look through a telescope. But today you can look at a telescope. So we'll be happy to take you in and show you some of our scopes and some of the images that we've taken with them. Also, if you paid to get in, if you go back to the gift shop, you'll get a card to come back on another night that has a better, well, you can come back on another night, and hopefully that night will allow you to also look at the night sky. So I want to thank you both very much for this just outstanding presentation. And come next week, we'll have hopefully maybe some students that may be going in your direction in a couple of years. This is the Southern Tier. Hold on, I'll just turn this off. I think that'll help. The Southern Tier Robotics Club will bring their competition robot here and show off what they do with theirs. So thank you all again for coming tonight, and we'll look forward to seeing you in the future. Thanks.